In Chapter 10, we're going to cover hypothesis testing. We're going to talk about it specifically for one sample, but hypothesis testing is going to be essential for everything that you're going to be doing in statistics from this level on. We're going to talk about the 5-step hypothesis testing procedure, and once you get that down, you'll be able to use that for any test that you're going to be doing in any kind of a statistical format. Beginning in Chapter 1, we talked about descriptive statistics and inferential statistics, and we said that inferential statistics allow us to estimate, generalize, or predict something about a population. We discussed or delved into it a little bit with z-scores and confidence intervals. Hypothesis testing, though, gives us a formal process to test our inferences or assumptions that we've made. Researchers will use hypothesis testing, for example, to test existing theories, propose new ones, test the effectiveness of a medicine or a social intervention, or just to compare two groups of observations. Hypothesis testing is used in business, medicine, social sciences, and many other disciplines, and it's essential in quantitative research. For many people, hypothesis testing can seem to be a kind of a difficult concept to grasp, but it's really not that difficult, especially if you follow the 5-step hypothesis testing procedure that I'm going to introduce in this chapter. And once you master that, you'll be able to use that with additional statistical computations that are coming up in additional chapters. So just hang on while we introduce the 5-step hypothesis testing procedure. The first step in the 5-step hypothesis testing procedure is to state the null and the alternate hypothesis. Hypothesis testing is going to take two hypotheses, the null and the alternate. At the end of the hypothesis testing procedure, the decision we make will be based on what we're doing with the null hypothesis, not the alternate. If you reject the null, then perhaps you could consider accepting the alternate, but really we report our research in terms of the null, what we end up doing, rejecting or not rejecting the null. So here's an explanation that'll hopefully make these make a little bit better sense. The null hypothesis is essentially the opposite of what we're really trying to discover in our research. So it's what we assume to be true, or it's the status quo, or it's common knowledge, or an established theory that we're trying to prove or disprove. The null hypothesis is always expressed in some form of equality, such as less than or equal to, greater than or equal to, or equal to. So here's an example. So let's assume that we think that we're being shorted in our bags of potato chips. Well, the null hypothesis would be that the chips, if it says on the bag 8.7 ounces, then we would assume that the null hypothesis would be that the amount of chips in the bag is greater than or equal to 8.7 ounces. Now we include the greater than because we want to ensure there's no lawsuits, and so the production company might throw in an extra chip or two to make sure that we're within tolerances, but the null is what's assumed to be on the bag, 8.7 ounces or more. We designate the null hypothesis with H sub 0, and the alternate hypothesis we designate with H sub 1. Mathematically, the alternate hypothesis is the opposite or contrary to the null. And since the null hypothesis always contains some form of equality, the alternate hypothesis will contain something like not equal to, greater than, or less than. So let's see how this works with our potato chips with both a null and an alternate hypothesis. All right, let's step through this with our potato chip company. So we assume that we are overseeing the production of potato chips. Every bag is labeled 8.7 ounces of chips. We need, though, to constantly monitor the chip dispenser and make sure that we are putting in at least 8.7 ounces of chips. If we put in too few chips, we're going to get a lawsuit, and we'll be sued and we'll be out of business. So we might think that there's a problem with the chip dispenser, and so we're going to actually go ahead and do some testing, and we're going to put in a hypothesis of both a null and an alternate. So the null hypothesis would be that the chip weight is greater than or equal to 8.7 ounces. Remember, we're going to put in an extra chip or two. We have a little tolerance to do that. Not too many or we'll go out of business. The alternate, on the other hand, is that the chip weight in the bags is less than 8.7 ounces. Again, we designate the null with H sub 0 and the alternate with H sub 1. Again, as I mentioned, we're really only concerned about underfilling the bags because we don't want to be sued. However, in the real world, overfilling the bags, as I mentioned, would also be a problem. Now, while overfilling the bags will make our customers happy, we're not going to stay in business to do that. So if you were actually a business student, you'll learn about tolerances in probably a production operations class. But typically our machine is going to have tolerances that we would work with. And so, for example, we might shoot for our chip dispenser of having a tolerance of maybe zero point 0.1 ounces, where we would allow anything from 8.7 to 8.9 ounces. But in this case, we're just simply saying we believe it's less than or greater than or equal to 8.7 ounces. So sorry to confuse you about that. Well, here's another example in how to develop the null and the alternate hypothesis. It's a food example. Must have been hungry when I was making these slides here. But assume in this case that we're working at a sandwich fast food restaurant, and we have one method for making a sandwich, and we have another method that's being proposed to us, and we want to find out which method is faster. So in this case, the null hypothesis, H sub 0, would be that the average assembly time for the new procedure is greater than or equal to the average assembly time for the old procedure. The alternate hypothesis would be that the mean assembly time for the new procedure is less than the mean assembly time for the old procedure. And again, the null hypothesis is what's assumed to be true. We're assuming that the old way is the best and that our new way is actually going to be greater. But we're testing the alternate and the null against each other to see which one actually is going to be the case. All right, so here's one more example in the field of medicine. So we'll assume that we're testing the effectiveness of a new medication, a new vaccine. And so our null hypothesis, remember, is what's assumed to be true or correct, or the status quo, is that the mean survival rate with the new treatment is less than or equal to the mean survival rate of the old treatment. Again, we're assuming the old treatment is the best. That's the null. The alternate is really what we're trying to discover here, is that the mean survival rate with the new treatment is greater than the mean or average survival rate with the old treatment. Okay, I think we've nearly beat null and alternate hypothesis to death here, so let's get back to the next step. Step 2 is to choose the level of significance. The level of significance is represented with alpha, and it is the probability of rejecting a null hypothesis when it's actually true. So to be considered statistically significant, the levels of significance that we use, they range from 0.1 to 0.01. Now, for example, choosing a level of significance of 0.05 would mean that we have only a 5% chance of rejecting a null hypothesis that is true. Therefore, we could essentially be 95% confident that we will not reject a null hypothesis that is true. Rejecting a null hypothesis when it is actually true is defined as a type 1 error. The level of significance is a chance of making a type 1 error. A type 2 error is when you fail to reject a null hypothesis when it's actually false. So, step number 2, choose the level of significance. For statistical purposes, the level of significance will range from 0.1 to 0.01. Step number 3 in the 5-step hypothesis testing procedure is to determine the test statistic you're going to use in testing your hypothesis and rejecting or not rejecting the null. So, we've learned about the Z and we've learned about the T up to this point. Now, in additional chapters that are upcoming, we're going to cover a few other test statistics that we can use. But for right now, this chapter will just talk about Z and T. The Z statistic we use when we know the population standard deviation, and the T statistic we use when we do not know the population standard deviation. Okay, moving right along, we're in step 4 of the 5-step hypothesis testing procedure, and that is to locate the critical value, and as it's most often called, the decision rule. The critical value is the value of the test statistic, for at least this chapter, Z or T, that you selected in step number 3. And you'll use that critical value of Z or T to determine whether or not you're going to reject or not reject the null hypothesis. Now, the critical value that you find will be determined on whether or not it's a one-tail test or a two-tail test. Now you can look at the null hypothesis and you can determine really easily whether it's a one-tail or a two-tail test. A one-tail test has only one mathematical direction. For instance, less than or equal to or greater than or equal to will be a one-tail test. A two-tail test is when you'll look in both directions, and that will have equals in the null hypothesis statement. So here's some examples of some null hypotheses to help us determine whether they're one-tail or two-tail tests. So the first example here is the mean chip contents is greater than or equal to 8.7 ounces. That is a one-tail test because we're only looking in one direction. Another example, the mean survival rate with the new vaccine is less than or equal to the mean survival rate without the new vaccine. Again, we're only looking in one direction for the testing of the null hypothesis. That's a one-tail test. A two-tail test example would be the null hypothesis is that our sandwich assembly new process is equal to the old process. In this case, we're looking for times in either direction. Now this will start to make a little bit more sense as we continue on here, so hang in there a bit. All right, finally, the fifth step is to take a sample and then compute the test statistic and then make a decision. The decision that we make is, are we going to reject or not reject the null hypothesis? Now, how we compute the test statistic is going to vary on what test statistic we're using. We've seen different examples already in computing z's and t's. So again, we're just going over the 5 steps here. We'll actually run through some examples now and see how this will work with different t and z examples. So in step 5, we're going to be computing the test statistic, and the way we make our decision is we compare what we compute to the critical value that we looked up earlier. So here's an example with a critical value of 1.96. So if the test statistic that we compute, let's say we compute a z of 1.5, well, that falls in the range of the do not reject area. On the other hand, if we compute a z-score of less than negative 1.96 or greater than 1.96, then we would reject the null hypothesis. All right, let's go ahead and step through a whole example of the 5-step hypothesis testing process. So we're going to use Dan's Deli as an example. So Dan's Deli makes great sandwiches and he's growing rapidly, but his customers are complaining that it takes too long to get their orders. So Dan knows that it takes an average, he's done a lot of research, it takes an average of 54 seconds to assemble a sandwich. And also from his past research, he's learned that the standard deviation of sandwich production is 0.7 seconds. So Marisol, one of Dan's employees, has come up with a new way to assemble sandwiches, and she says it's faster. Dan's a little skeptical, but he's decided to test it. So he's going to go through the 5-step hypothesis testing procedure to see if Marisol's method might be better than the existing method that he's been using to assemble his sandwiches. Okay, so going through the 5-step hypothesis testing procedure, step number 1 for Dan is to state the null and the alternate hypothesis. So the null hypothesis in his case is that there's no difference, that the way he's been doing it, the population mean is going to be exactly the same as the new method that Marisol has proposed. The alternate hypothesis is that there is a difference. Step number 2 is to select the level of significance. So Dan selects a 0.1 level of significance. That means that there is a 10% chance of him making a type 1 error and rejecting the null hypothesis when it's actually true. Step number 3 for Dan is to determine the test statistic. Well, from his previous substantial research, he already has a population standard deviation, and so that means he can use the z statistic. Next, he's going to determine step number 4, the critical value or the decision rule. So this is a two-tailed test because he's pretty sure that the time is going to be the same for both. So let's go ahead and see how he's going to come up with the critical value. So to determine the critical value, we need to know what the level of significance was. Remember, that was 0.1. So it's a two-tailed test, so he has to divide that 0.1 by 2, which means there's going to be 5% in each tail. So the do not reject area is going to be 0.45 on each side. So now we need to look up the area of 0.45 in the standard normal distribution table to figure out what the critical z-score is going to be. So we've determined that we're looking for an area of 0.45. So we examine the standard normal distribution table and we notice that it's not there. So we end up seeing that there's a close z-score of 1.64 and 1.65. It's somewhere between there. And so we're actually going to kind of average those two together, and we're going to end up with a critical value of 1.645, which is halfway between those two listed z-scores. All right, so just a quick review of what we've done so far. We've determined the null and the alternate. The null is that they're equal. The alternate is that they're not equal as far as the sandwich assembly times. We have a level of significance of 0.1, which means there's 5% in each tail. So we come up with a critical value of 1.645. We're going to then compute the z-stat and compare that to the critical value of 1.645 to determine whether we will reject or not reject the null hypothesis. So Dan is now ready for the fifth and final step in the hypothesis testing procedure. He's taking a sample, he's going to compute the test statistic, compare that to the critical value, and make a decision. So for the sample, he came up with a mean assembly time of 53 seconds using Marisol's revised method. So he's going to compute a z-score. Remember, he does have the population standard deviation, and so he uses this formula, and he ends up with a z of negative 4.512. Well, that z-score falls way outside of the reject area. In other words, it's far greater in absolute value than 1.645. And so he is forced to reject the null hypothesis. And he then concludes at the 0.1 level of significance that there is a statistically significant difference between the old method and Marisol's proposed assembly methods. So based on that result, he decides to promote her and encourage her to look for even more ways to increase efficiency because he's going to adopt her method. All right, let's run through another example. This is with an unknown population standard deviation. So Cindy is a high school senior, and she's thinking about attending a private college that's nearby, and that private college advertises that they are very generous in their scholarships and grants. In fact, on their website, they say that their average graduate only owes $5,000 in student loan debts when they're done with a 4-year degree. Cindy thinks that this is probably not correct. In fact, she thinks that's probably too low, and so she decides to test the hypothesis. So she's going to survey 15 college seniors a month from their graduation, and she's going to ask them how much they owe. So her null and her alternate hypothesis are this. The null hypothesis is that the average student loan debt is less than or equal to $5,000. That's what they're advertising. That's what is assumed to be true. The alternate is that their average loan debt is greater than $5,000. So she's going to put that to the test. Step number 2 in Cindy's 5-step process is to select a level of significance. So she selects a level of significance of 0.05. That gives her only a 5% chance of rejecting a null hypothesis when it's actually true, which is called a type 1 error. Number 3, determine the test statistic. She doesn't know what the population standard deviation is. She only has the mean. So in this case, she's going to use the t statistic. Next, for step 4, Cindy has to determine the decision rule or the critical value. This is a one-tailed test because she's only testing one direction. So to find the critical value, because she's using the t, she has to determine the degrees of freedom. The degrees of freedom are going to be n, the sample size, minus 1. So with a sample size of 15, the degrees of freedom are 14. We have a 0.05 level of significance with 14 degrees of freedom, and so we're going to find a critical value on the table. Using the t distribution table, we then are looking at the one-tail row with a 0.05 level of significance. We scroll down till we find the degrees of freedom of 14, and we end up then with a critical t value of 1.761. All right, Cindy is ready now for the final step in the hypothesis testing procedure. She's taken a survey of 15 students, and she's found that they owe an average of $5,415.33 in student loans. Now, at first glance, that is larger than the $5,000 that the school advertised. So she's beginning to think in her head that, okay, my assumption is probably correct, and I'm going to be able to reject the null hypothesis. But we can't do that until we run through the numbers. So she computes a t-score using the t-score with one sample, and she ends up then with a t-score of 0.48046. Well, what does that mean as far as rejecting or not rejecting the null? Let's look on the next slide. Well, comparing the t-stat that she computed of 0.48, it's less than 1.791, which means it falls in the fail to reject the null hypothesis area. It has to be greater than, an absolute value greater than, either more negative or more positive than the critical value. So even though her sample average is higher than the $5,000 they reported, she cannot conclude at the 0.05 level of significance that the mean student loan debt is greater than $5,000. So she fails to reject the null hypothesis. All right, let's run through this and try to figure out why she could not reject the null hypothesis, even when the sample mean that she computed of $5,400 approximately was significantly higher than the $5,000 advertised by the college. The reason for this is that she chose a 5% level of significance. A 5% level of significance, 0.05, means that she will only tolerate a 5% chance of making a type 1 error. Now the t-stat that she computed was 0.48046 with 14 degrees of freedom. The probability of making a type 1 error, now we'll refer to that as the p-value, with that t-stat is actually 34.47%. That's much higher than the error that she was willing to tolerate. And because that is higher than what she's willing to tolerate, she's not willing to tolerate a 34% chance of making a type 1 error. She will not reject the null hypothesis. Now, if you ever want to compute a p-value from a t-stat, Excel has a function. Excel's function, the t.dist function, you just pop in the t-stat that you've computed with the degrees of freedom, and it will then give you the probability of making a type 1 error, or the p-value for that t-stat. Well, let's try one more example of the 5-step hypothesis testing procedure, this time using a proportion. So a recent study that Mario was reading reported that 33% of college students changed their major within the first 3 years of college. Well, Mario doesn't believe that that's that high at his college, and so he decides to test this hypothesis, and so he surveys 50 seniors at the college that he attends to see whether or not they have changed their major or considered changing their majors. So his null and alternate hypothesis is: the null hypothesis, the proportion of seniors who change their major is greater than or equal to 33%. The alternate hypothesis, the proportion of seniors who change their majors is less than 33%. He selects a level of significance. He decides to go with a 0.05 level of significance, which gives him a 5% chance of making a type 1 error. Well, he determines a test statistic, which will be the z-stat, because he is working with a proportion. All right, step number 4 for Mario is to determine the critical value, or the decision rule. This is a one-tailed test because he's only looking for one direction, which is less than 33%. So he's looking for a z-score that equates to an area of 0.45. And of course, as we found out in the previous example, that value is going to be 1.645, which is halfway between 1.64 and 1.65. All right, the final step is to take a sample and compute the test statistic. And so he surveyed the 50 seniors. He ended up with a 20% proportion, 0.2. And so using the formula to compute a z-score for one proportion, he computes a z-score of negative 1.955. And this is more negative or larger absolutely than the critical value that he came up with. So in this case, he will reject the null hypothesis and conclude that possibly his school might have better stats than the reported proportion. All right, some concluding thoughts. Let's review quickly what we talked about in this chapter. We introduced you to the 5-step hypothesis testing procedure. Step number 1, state the null and the alternate hypothesis. Remember, the null is what's assumed to be true. The alternate is what you're proposing potentially. Step number 2, choose the level of significance, which is the chance of making a type 1 error. Determine the test statistic. For this chapter, we just talked about Z and T. We will learn more as we continue on. Locate the critical value that equates to your level of significance. Take a sample and compute the test statistic. We saw that there were different formulas for a z-stat. When we know the population standard deviation, we simply take the x bar minus the mu divided by the standard deviation divided by the square root of n. We also discussed in this chapter, when we do not know the standard deviation of the population, we use the t-stat, and we also computed the z-stat for proportions, and the formulas are given to you on the screen there. And remember, all of these lessons are based on my textbook, Surviving Statistics, which is available on Amazon. And do remember to check out my website for downloadable files, calculators, and other resources.